Very good day to all of you. Today we are going to look at the triple integral in spherical coordinates. Okay, look at it. This is a 3D graph where this is a x-axis, y-axis, z-axis, and this is a row. Make an angle phi with the z-axis. Okay, and this line is the r. It's actually radius of a circle. R, make an angle theta with your x-axis. This is the y-axis. So if you look at here, this is R, this is theta. So y is here, x is here. Okay, as you learn in the polar coordinate or spherical coordinates, okay, we have the x is actually the r cos theta, y is equal to r sin theta. That is in the polar coordinate. And by taking the cos theta, we have the x over a. That's why x is r cos theta. By taking sin theta, which is y over r, that's why y is r sin theta. Okay, when r here, when you raise up, this is about this is a z. When this is z and parallel here, this is z. So when the r you raise up to a height z, so this one is actually the r. I'll put it in 2D. R is here. Rho is actually the radius of a sphere, where the rho squared is actually the x squared plus y squared plus z squared. Okay, so z. So in 2D, you look at here. Okay, rho is the radius of a sphere. Make an angle phi with the z-axis, and this is the r. Okay, by taking the sin phi, sin phi will be r over rho, or r is actually rho sin phi. R is actually rho sin phi. Okay, by taking cos phi, from here cos phi will be z over rho. Hence, z is a rho cos phi. So now, we have this now. R is actually rho sin phi. Or from polar coordinate, you know that r squared is actually third x squared plus y squared. And in spherical coordinate, here r is actually rho sin phi, where the rho is actually square root of r squared plus z squared, or equal to, how I get rho is square root of r squared plus z squared is from this triangle. Rho making an angle phi with z. Okay, and this is r is actually r on 2 xy plane. When you raise up and with a height z, this is actually the r, and this is actually 90 degree here. This one no. So that's why in the r squared plus z squared equal to rho squared. So that rho squared is actually r squared plus z squared. And you know r squared is actually x squared plus y squared. That's why rho is actually, rho squared is x squared plus y squared plus z squared. Or rho is actually radius of a sphere. Okay. And from the polar coordinate, as you know, that x is r cos theta, and r is actually rho sin phi. That's why you have here. This is r cos theta. Means substitute r equal to rho sin phi. That's why x in spherical coordinate means x you change it to rho sin phi cos theta. From y equal to r sin theta in polar coordinate, and you know that here r is rho sin phi. That's why r become rho sin phi sin theta, and z is rho cos phi. Okay, it's from this angle, this triangle. This triangle, with z making an angle phi with the rho. Okay, r is here, which is actually r is when you raise up at z, okay, unit, this is the r, taking sin v, okay, because this is right, okay, 90 degree here, taking sin v will be r over rho, or r is rho sin v. Taking cos v is z over rho. Okay, that's why z is rho cos v. And basically, we have z is rho cos v, r is rho sin v, and from polar coordinate x is r cos theta. Replace r by rho sin v, okay, and then become cos theta. Y is r sin theta, and r is rho sin v sin theta. And rho squared is actually x squared plus y squared plus z squared. Okay, that's why, okay, conversion formula from Cartesian to spherical coordinate. X is actually rho sin v cos theta. Y is rho sin v sin theta. Z is rho cos v. X squared plus y squared plus z squared equal to rho squared. Okay, where the v is actually from 0 to pi. V is measured, okay. Notice that v is measured from positive z, okay, until negative z, so it's only, okay, half cycle. That's why v, okay, from positive z until negative z will come 0 to pi only. Okay, theta is measured, okay, horizontally as in a polar coordinate or spherical coordinate. Full cycle will be 0 to 2 pi. Okay, for example, 1. Set up the limit to find the volume of a sphere x squared plus y squared plus z squared equal to a squared by using Cartesian coordinates. Okay, sphere, you notice that coefficient for x squared, y squared plus z squared are positive and have the same coefficient. Okay, so this is a sphere, okay, with radius a unit, mean the rho will be equal to a. Okay, but this example want you to set up the limit to find volume. Okay, set up limit only using Cartesian coordinate. Okay, if you use Cartesian coordinate, okay, if you, okay, the sphere is parallel with the z-axis, okay, as in the previous lectures, you know that to find the volume in Cartesian coordinate, we have 6 orientation. Okay, one of the orientation, if let's say if you view, okay, your volume here or solid G is parallel with z-axis, then you integrate with dz first. Then, okay, after you want to integrate, okay, respect to dz first, then you need the limit of z. To get the limit of z, okay, from the sphere equations here, okay, you solve for z. Okay, from here you solve it, okay, for z. That's why you have the, okay, when the z squared equal to a squared minus x squared minus y squared. Okay, and then we're taking here square root. That's why I have z is actually negative square root of third a squared minus x squared minus y squared. Okay, will be the lower surface of the z, or the lower hemisphere. Z, okay, equal to positive third a squared minus x squared minus y squared. Okay, it's actually the upper hemisphere. Mean, okay, imagine your, okay, sphere, if you cut it at, okay, z equal to 0, you have the upper surface, which is given by this one, upper hemisphere. Okay, lower surface, which is given by lower hemisphere. Okay, so this is the limit for the z. Limit of z there, where you put it here. Okay, volume is actually triple integral 1 dv. dv we use dz dy dx. So this is a z equal to negative third, okay, negative third a squared minus x squared minus y squared up to z equal to positive third a squared minus x squared minus y squared. Is actually lower hemisphere until upper hemisphere. Okay, after you dz, okay, when you press your sphere, okay, you have your projections R, the dA. dA is depend on your region R. Okay, your sphere, okay, the projections will be a circle, right? You'll get a circle. Okay, how do you get the circle? Okay, the projections will happen when you let z. Okay, because you press it. Okay, so it will be z equal to 0. So if you have x squared plus y squared equal to a squared is actually a circle centered at origin with radius a units. So you get circle, this circle, right? And this circle is actually you have the two curve. The bottom curve is this one, the blue color. Okay, top curve is the red color. Okay, the blue curve, okay, how you solve it? Okay, for the blue curve, from the circle x squared plus y squared, okay, equal to a squared. Okay, how we obtain this one? Okay, region R is your z equal to 0. Then z is 0, x squared plus y squared equal to a squared. Okay, solving for y, we have y, okay, is positive negative third a squared minus x squared. So this case is a lower curve, this is the upper curve. In the lower curve, the blue color is actually y equal to negative third a squared minus x squared. Okay, and then the red color curve, upper curve is actually y equal to positive third a squared minus x squared. Okay, and okay, this is a circle, the x-intercept from negative a to a. We have the full circle. If we use dy dx, it's actually we integrate using, we sum the area using vertical bar. And you're going to sum the vertical bar from left side, which is x equal to negative a until x equal to positive a. Okay, so okay, limit for y is actually the blue color, the lower curve, which is y equal to negative third a squared minus x squared. Okay, up to the red color curve, which is y equal to third a squared minus x squared. So this is a limit here for finding the volume of a sphere in Cartesian coordinates. Okay, the question is actually set up limit. We just keep it here, but okay, I just would like to show you what is the problem if we find the volume of a sphere using Cartesian coordinate. Okay, so to evaluate this triple integral, you have integrate 1 respect to z. You have z. Okay, plug in the upper limit, okay, minus the lower limit. Okay, so minus we have 2 times third a squared minus x squared minus y squared. Okay, notice that this one cannot be integrated. That's why to find the volume of a sphere in Cartesian coordinate, we face a problem to integrate it. Okay, hence example 2, the same problem. To find the volume of a sphere x squared plus y squared plus z squared equal to a squared, but this time we use spherical coordinate. Because if we use Cartesian coordinate, we face difficulty to integrate, cannot integrate. Okay, so the same thing, we use the volume dv as dz dy dx. Okay, and then in spherical coordinates, dy dx become r dr d theta, and the x squared plus y squared will be r squared. Okay, that's what. Okay, spherical coordinate actually maintain the z, but dy dx change to dr. Okay, dy dx become r dr d theta. Okay, so this term, okay, this is actually minus. Okay, if we factor out the negative, so minus x squared plus y squared. In the same problem now, we are going to use spherical coordinate. So the limit for z now, if using spherical coordinate, will become negative third a squared minus, because the x squared plus y squared will be replaced by r squared. So limit for z is from negative third a squared minus r squared until positive third a squared minus r squared. And from Cartesian, we change it to spherical. Okay, this is here lower hemisphere, z equal to negative third a squared minus r squared up to z equal to positive third a squared minus r squared. Okay, still same with Cartesian. only x squared plus y squared will change to r squared. Okay, and dz in cylindrical coordinate, dz maintain, dA become r, dr, d theta. Okay, so we need the limit of r. Okay, from the circle just now, x squared plus y squared equal to, okay, a squared. So you have the r squared equal to a squared. So r equal to a. Okay, just now we have the full circle. Full circle. That's why a from 0 until the radius of the circle 0 to a. And it's a full circle. That's why theta 0 to 2 pi. Okay, that's why r 0 to a, theta 0 to 2 pi. Okay, now again let's integrate in cylindrical coordinate. So integrate r respect to z. Okay, so you have r times z. Because integrate respect to z, plug in into variable z. Okay, again plug in. Okay, this one sud a squared minus r squared minus with negative. So you got 2 times sud a squared minus r squared. Okay, to integrate, okay, sud a squared minus r squared r dr. We use a substitution, means we replace the a squared minus r squared with u. U is a squared minus r squared. Okay, we want to integrate respect to r. So from u, you find du dr will be negative 2r. That's why du is negative 2r dr. Okay, you notice that you have the term r dr. Okay, that's why r dr become negative du over 2. Okay, so the integral of sud a squared minus r squared r dr, when the r dr you change to du over negative 2. Okay, a squared minus r squared, okay, power half become u power half. So integrate negative, okay, half u power half become negative half u power. In integration, the power increased by 1, so u power 3 over 2 divided by the increased power, which is 3 over 2. Okay, simplify it, got 2 and 2 here cancel. You get negative u power 3 over 2 over 3. So that's why here, this is another way shortcut without using. You get the result negative, okay, 1/3 a squared minus r squared power 3 over 2. You replace back the u is here. Okay, so this is the result of the integral of sud a squared minus r squared r dr using substitution technique, and plug in the r for integrate respect to r, plug in the limit of r from 0 to r. Okay, so plug in into r. Plug in upper limit a squared minus a squared, you have 0. Okay, minus with substitution of a lower limit. So a squared minus 0, power 3 over 2, so 2 and 2, you cancel, you got a cubed minus a cubed. So negative, negative, so you got 2a cubed over 3, integral of d1 d theta from 0 to 2 pi, you get this is 2 pi. 2 pi times 2a cubed over 3, you get 4 pi a cubed over 3, which is tally back with, okay, formula of volume of a sphere is equal to 4 pi r. Okay, r is the radius of a sphere. In this case, radius of sphere is a. So 4 pi a cubed over 3. We tally with the formula of volume of a sphere, which is 4 pi r cubed over 3. 4 pi r cubed over 3. And this question, the radius, okay, of the sphere is a. That's why you get 4 pi a cubed over 3. This is using cylindrical coordinate. Okay, now, since our topic is solve triple integral in spherical coordinate, okay, I just purposely use the simplest example, sphere, volume of a sphere, go through Cartesian coordinate. You notice that you face difficulty to integrate. Okay, in use cylindrical coordinate, okay, you can integrate and get the result. Now we're going to use a spherical coordinate. Okay, the same problem, the same sphere, x squared plus y squared plus z squared equal to a squared using spherical coordinate. Okay, so it knows that x squared plus y squared plus z squared is actually rho squared. So rho squared equal to a squared. So rho equal to A. So rho is actually from 0 to A. This is your sphere. This is your sphere. Yes, so the rho is actually from the center of your sphere, okay, up to the radius here. From 0 until A, the rho. Okay, when you rotate, the radius of a sphere is always, maximum is A. Minimum is from the origin, which is 0. Okay, how it gets the phi? Phi, remember just now, phi is measured from, okay, this is actually, here is Z. Phi is measured from positive Z. Okay, phi making an angle, positive Z axis with the radius of a sphere. Okay, but the sphere, if you take it actually, half cycle, that's why phi 0 to pi. Okay, theta is actually we rotate, okay, in the circle here, we rotate, okay, horizontally. We rotate horizontally the yellow color, so theta is 0 to 2 pi. Okay, you can touch, okay, an orange. Rho is actually radius of that orange, okay, of the orange, okay. And then phi, you touch it from top surface of the orange until bottom surface is half cycle. So phi 0 to pi. Theta, okay, it takes the orange, rotate it, okay, horizontally. So one cycle, full circle. So 0 to 2 pi. Theta is same as in the polar coordinate or spherical coordinate. In theta, you can measure it in 2D. Phi 3D, from Z positive until Z negative, that's why phi 0 to pi. Hence, K volume, okay, is given by triple integral 1 dV. Okay, dV, just now, okay, said that for dV is actually, yeah, dV is rho squared sin phi d rho d phi d theta. dV in cylindrical is dz r, dz dr d theta. The second example, dV, okay, it is you have dz, means cylindrical we maintain z, dz. Then r dr d theta is actually dA in polar coordinate. Okay, but in spherical coordinate, dV is actually rho squared sin phi d rho d phi d theta. Okay, we just use it, okay, we skip the proof. So hence, okay, now integrate rho squared sin phi d rho. When you integrate respect to rho, phi and theta are constant. So you integrate rho squared respect to rho, you have rho cubed over 3. So I factor out 1/3 outside. Simply just okay, because it's constant. So it remains there since phi. So limit for rho 0 to A. So plug in the limit. So you have A cubed minus 0, you get A cubed. So you come A cubed over 3. And after you plug in here, you get A cubed over 3, and then left integral of sin phi d phi. Integrate sin phi, you get negative cos phi from 0 to pi. Okay, plug in pi, cos pi is negative 1. So negative 1 and negative become positive 1. Minus, okay, cos 0 is 1, so that's why I get negative 1. So 1 minus negative 1, I have 2. So 2a cubed over 3. Integrate 1 d theta from 0 to 2 pi, get 2 pi, so total get 4 pi a cubed over 3. Compared to cylindrical coordinate, we have a simpler integrand to be integrate. Because using cylindrical, we met with square root a squared minus a squared, where you need to solve using substitution technique. But you use spherical coordinate, you easily integrate it without difficult integral. And just integrate rho squared rho cubed over 3, plug in limit, you get here. Thus we integrate sin phi dphi, you get negative cos phi. Okay, and then take note here, the cos phi is equal negative 1. So negative 1, negative positive 1. Cos 0 is 1. 1. So negative 1. So you have since 3 example, finding volume of a sphere, go through Cartesian coordinate, you cannot integrate it. Spherical coordinate, okay, still can be integrated, but if you face a little bit difficulty to integrate, you have to solve it using substitution technique. If you use spherical coordinate, then easily you can integrate it. Okay, normally if the solid involved of sphere, hemisphere, or combination of sphere and cone or cone, then we use spherical coordinate. Okay, example 4, use spherical coordinate to find the volume of the solid bounded above by a sphere x squared plus y squared plus z squared equal to 6 and below by cone z equal to third x squared plus y squared. We have solved this problem in spherical coordinate, okay, in last lectures. So basically, your solid, you have, okay, cone. Okay, at the bottom surface is a cone, z equal to third x squared plus y squared. Okay, it looks like your ice cream cone. Upper is the ice cream, which is given by the sphere equation, x squared plus y squared plus z squared equal to 16. We want to find the volume, and we notice that this solid is parallel with z-axis, so we integrate it respect to z first. Okay, in this case we use spherical coordinate. Then dv is a rho squared. Okay, dv rho squared sin phi d rho dv d theta. Then you need the limit for rho, limit for your phi, limit for your theta. Okay, to get the limit of rho, solve your sphere equation. X squared plus y squared plus z squared will give you, okay, rho squared equal to 16, or rho is actually 4. Rho is actually 4, so mean, okay, the rho is actually from here until the radius of your sphere, which is equal to 4. That's why rho 0 to 4. How to get the phi? Phi is actually the angle from positive z-axis until we touch the surface of cone, z equal to square root x squared plus y squared. So solving the cone equation, okay, this is actually the upper cone because z is positive. Okay, if z, okay, upper cone, then you have only, okay, cone like this. Okay, only one cone. Okay, if z squared is actually you have, okay, you have the upper cone and bottom cone. Bottom also gone. So z equal to third x squared plus y squared, only upper cone. Okay, to get the phi, we need to solve that cone equation because phi is actually from positive z-axis. Okay, you rotate until touch, okay, the surface of the cone. Touch the surface of the cone here, from here until here. So what is the angle that there is a phi? So to get the phi, we need to solve the cone equation. When we square it, you get this. Z squared is x squared plus y squared, and you know that z is rho cos phi. That's why z squared is rho squared cos squared phi. X is rho sin phi cos theta. So you square it, rho squared sin squared phi cos squared theta. Y is rho sin phi sin theta. So effect, okay, both x squared and y squared term, you have the, okay, same term, rho squared sin squared phi. This one factor out. So actually y is rho sin phi sin theta. This is a square. Okay, and cos squared theta plus sin squared theta is actually equal to 1. This one 1. Cancel rho squared at both hand side. So you have actually tangents, okay, Then you got the tangent squared is actually equal to 1. Right? Sin squared phi divided by cos squared phi gives us tangent squared phi equal to 1. Hence, tangent phi is 1, phi equal to pi over 4. Okay. So your phi is 0 to pi over 4. Cos of opposite z-axis, phi is 0 until touch the surface of cone. Okay, by solving this cone equation, you get the phi is pi over 4. If you have different coefficient of a cone equation, your phi will be different than pi over 4. Depend on the cone equation. You have different phi. Okay, how do you get the theta 0 to 2 pi? Because the projection of the cone, okay, projection of the cone, you have the circle, and this is a full cone, the projection is full circle. That's why theta is 0 to 2 pi. So dv rho squared sin phi d rho d phi d theta, rho from 0 to 4 by, okay, because our sphere is radius 4 unit. Solving the cone equation, you get phi 0 to pi over 4. The projection of the cone is full circle, so theta from 0 to 2 pi. So again, integrate rho squared sin phi d rho. You have rho cubed over 3. Sin phi is constant. Leave it there. Plug in the limit of the rho. 4 power 3, you have 64 over 3. Integrate sin phi, you have negative cos phi from 0 to pi over 4. Okay, and then plug in cos pi over 4, sec 2 over 2. So minus cos 0 is 1, so minus negative 1. Okay, so negative 1, okay, negative is positive 1, positive 1. Okay, make it become, okay, this one you times 2, you divide by 2. Let's have 2 minus sec 2 over 2. Okay, so constant we have here. Then 2, 1, 2, cancel with 64, you get 32 over 3 times 2 minus sec 2. Integral of 1 d theta from 0 to 2 pi give you 2 pi. So total 32 times 2 pi, 64 pi times 2 minus sec 2 over 3. Okay, example 5. Use the spherical coordinates to find the volume of the remaining solid by drill out the solid bounded above by sphere x squared plus y squared plus z squared equal to 16 and below by cone z equal to sec x squared plus y squared in the sphere of x squared plus y squared plus z squared equal to 16. Okay, exactly. Look at this one. We have a sphere. Okay, with radius 4 unit, where we have 5, so okay, the volume in example 3, volume of a the volume of a sphere in example 3, but in the with the okay the radius is 8. Now radius is 4, and then we have find the volume of a cone where the upper surface is a cone, and you notice that the same cone equation z equal to sec x squared plus y squared. So if you want to find the white color, okay, this is in the example 4 just now. Example 4 just now. Now what we want to find is actually the volume of the gray color by drill. Okay, when you have a sphere, drill out the volume of a ice cream cone. You left out the gray color. So you notice that in the previous, in this example 5, example 4, we have found the volume of the ice cream cone, where the phi is actually you solve the cone equation just now. Phi you get this same cone equation, you get the phi pi over 4. Okay, the example 4. Rho 0 to 4, because it's we have the same sphere as a top surface. And what we have is here the same sphere, okay, but phi is up to the cone equation. So you see, sir, rho 0 to 4, phi 0 to pi over 4, theta 0 to 2 pi. Okay, in example 5, what we want is actually the volume after you drill out the cone in example 4. Example 4. In the left out the gray color, the solid, okay, for the gray color. So the row will be the same because it's the same sphere. So row from 0 to 4. The same. Row 0 to 4. dv rho squared sin phi d rho dphi d theta. Okay, theta still 0 to 2 pi because the projection is still have a full circle. Theta from 0 to 4. Okay, you notice phi is from pi over 4 up to pi. Okay, look at the gray color here. Because it's a remaining solid that we want to find. It's actually, okay, the white color in the previous example, example 4, the phi, okay, is actually making angle from positive z-axis until your cone up to here. Phi is pi over 4. Okay, we want the solid, okay, by drill out your, okay, ice cream cone here. So mean it's actually from phi equal to pi over 4 until phi equal to pi. So you see the difference here. If you want to find the volume of a sphere with radius 4 units, rho is in, okay, dv here same. I repeat one more time. If you want to find the volume of a sphere with radius 4 units, your rho 0 to 4. The phi will be 0 to pi. Theta 0 to 2 pi. If you want to find volume of a sphere, phi 0 to pi. Okay, you want to find volume of a hemisphere, phi 0 to pi over 2 because half. Okay, then if you want to find volume of an ice cream cone where the top surface is a sphere with 4 units, okay, and your cone equation is z equal to sec x squared plus y squared, then the phi is from 0 to pi over 4. Okay, but this case is a volume that remains after you drill out this ice cream cone. So phi is from pi over 4 until pi. So there is a difference. I hope you can digest it and understand yourself. Okay, I'm not going through the same detail of the integral because it's same procedure. Only we change phi now from 0 to pi over 4 to pi over 4 to pi. Okay, example 6, okay, we have the Cartesian coordinate and we have to change it to spherical coordinates. Okay, so to change it, dz dy dx become rho squared sin phi d rho dphi d theta. Okay, x squared plus y squared plus z squared will be rho squared. Taking the square root, it become rho. Z squared will be rho squared cos squared phi. So okay, 1, 2, 3, you multiply it, it become, because z squared times this square root times dz dy dx is, you multiply 1, 2, 3 here. Total you have rho power 5 cos squared phi sin phi d rho dphi d theta. Okay. So total this thing, you get rho power 5 cos squared phi sin phi d rho dphi d theta. So how to determine the limit for rho, phi and theta? Okay, to determine the limit for rho is normally you need to find your sphere. Okay, sphere. Okay, or from limit for z 0 to square root 4 minus x squared minus y squared. Yeah, limit. Okay, this one lower limit of z, upper limit of z. Okay, from upper limit of z, when you square it, you will have z squared. Okay, from less than equal, make it equal. When you square it, z squared equal to 4 minus x squared minus y squared. Okay, or you have x squared plus y squared plus z squared equal to 4. Okay, this one, the equation z equals 4 minus x squared minus y squared is actually upper hemisphere. Mean from x squared plus y squared plus z squared equal to 4, if you cut it at z equal to 0, you have the upper hemisphere where the equation is z equal to positive third 4 minus x squared minus y squared. If it takes a lower surface, which is the lower hemisphere, z will be equal to negative third 4 minus x squared minus y squared. Okay, solving, and then when you square both hand side, this is actually sphere equation. Sphere. So x squared plus y squared plus z squared actually your rho squared. So rho squared equal to 4, so rho equal to 2. So rho from 0 to 2. Okay, since from the limit for z, we have z from 0. Lower surface is z0. Upper surface is z equal to third 4 minus x squared minus y squared. So this tells you the solid is actually upper hemisphere. That's why phi is 0 up to pi over 2. Okay, phi, because you have an upper hemisphere, for example. Okay, upper hemisphere, okay. And then to find the phi, you rotate here. Only because this is z positive half. You don't have the negative. So only half. So that's why phi 0 to pi over 2. If you have the full sphere, then phi 0 to pi. Okay, so you got the limit for rho, limit for phi. How to get limit for your theta? Limit for the y, okay, from the integrand, limit for y is actually negative third 4 minus x squared until positive third 4 minus x squared, x from negative 2 until positive 2. Okay, exactly here, this limit for y. Okay, lower limit is actually, lower limit of y is actually, okay, here, let's say a blue color, this one. Is y equal to negative third 4 minus x squared. Okay, upper limit of y is actually the upper curve. Y equal to third 4 minus x squared. And they said x from negative 2 until positive 2. That's why your region R is a full circle. So theta will be 0 to 2 pi. That's why that full circle theta 0 to 2 pi. Okay, from the limit of z, we have z0 until z equal to third 4 minus x squared minus y squared. It tells you this one is the upper hemisphere. Okay, this surface tells you this is upper hemisphere. Here. Okay, so upper hemisphere phi 0 to pi over 2. If sphere phi 0 to pi. Okay, you square, the upper hemisphere, you get this is a sphere with radius 2 units. That's why rho 0 to 2. Okay, and this one, we have solved it just now. You get rho power 5 cos squared phi sin phi d rho d phi d theta. So integrate respect to rho first. So you got rho power 5 become rho power 6 over 6. Factor out 1 over 6. Substitute into rho. So 2 power 6, 64 divided by 6, you get 32 over 3. Integrate cos squared phi by using substitution technique. We get negative cos power 3 phi over 3. Okay, phi from 0 to pi over 2. Okay, cos pi over 2 is 0 minus sin 0 is 1. So I have negative 1. So negative, negative, positive 1. So you got 32 over 9. Integrate 1 with theta, you have 2 pi. So total is 64 pi over 9. Okay. To integrate cos squared phi sin phi d rho, we use substitution where u is cos phi. Okay. So you find du dphi will be negative sin phi. Okay. So du is negative sin phi dphi. So integrate cos squared phi will become u squared, where the sin phi dphi will become negative du. So that's why you have integrate negative u squared, you get negative u power 3 over 3. Substitute back your u is cos power 3 3 over 3 here. Okay. Okay, the next example, the same with example 6, but this one same, here same, okay, z0 until z equal to third form minus x squared minus y squared. Okay, limit for z tell you is still upper hemisphere solid, but is it full upper hemisphere? Okay, you have to confirm it from the limit for y. Limit for y tell you is 0 to third form minus x squared. Okay, limit for y, okay, tell you y0 until y equal to third form minus x squared. So, okay, it is actually here, semicircle, but is it full semicircle? You have to confirm it from limit for x. Negative 2 to 2, negative 2 to 2. So it's a full semicircle. Semicircle. Okay. So your theta in this case is 0 to pi. The rest are same. 0 to pi. Rho same, cos you still have the same, okay, upper hemisphere. Phi, because from upper hemisphere, there's a phi says 0 to pi over 2. However, limit for y tells you the projection is only semicircle. Semicircle. That's why theta from 0 to pi. Okay, the rest of the calculations still the same. Example 8, still same, but now that x from 0 to 2, y from 0 to third form minus x squared. Limit for z still same. Limit for z same, so means you still have the same upper hemisphere. Okay, however, the projections dy dx here tells you y from 0 to third form minus x squared. Okay. Okay, this is y equal to 0 until y equal to third form minus x squared. Okay, from limit of y will tell you actually you have a semicircle. However, limit of x from 0 to 2. In this case, 0 to 2. 0 to 2. Hence, is only quadrant of circle. That's why theta in this case is only 0 to pi over 2. Okay, that's why, okay, everything same. Rho, cos, okay, your upper hemisphere, okay, the radius is 2. Upper hemisphere, phi still 0 to pi over 2. However, your upper hemisphere is only, the projection is only, okay, quadrant of circle. Okay, mean this example is actually, you don't have the full hemisphere, but have 1/4 of the full, 1/4 of your hemisphere. Okay, and example 7, this one is actually you have half of your upper hemisphere. Half. Because you cut it by y equal to 0. Half of the upper hemisphere. Example 6, this one negative third form minus x squared. You have full upper hemisphere. Okay, and then we have the last example. Use spherical coordinates to evaluate. Also in Cartesian coordinate and change it to spherical coordinate. So this dz dy dx you change it to rho squared sin phi d rho d phi d theta. Okay, limit for z tell you, okay, this is a cone, and the cone is cut. Okay, this time the cone upper surface is flat. Z equal to 1. Compared to previous example, cone upper surface is your sphere or upper hemisphere. Great. So limit for z. So mean this is a cone. Okay, top is actually z equal to 1. Z equal to 1. Okay. So we don't have the sphere. don't have the sphere, so how to find your rho? From z equal to 1, z is rho cos phi equal to 1. So cos phi we bring to right hand side become 1 over cos phi is a secant phi. So in this case your rho is 0 to secant phi. Because rho actually you measured from origin until we touch z equal to 1. Okay, this time not compared to just now the ice cream cone, the rho is actually it's a round, it's a radius of a sphere, but in this case the rho is actually touch the z equal to 1. That's why rho solving the z equal to 1 equation you get rho from 0 until secant phi. Okay, to get what is a phi, again solving the cone equation here. This is a phi. To get phi, you solve the cone equation as just the previous ice cream. The cone with the upper surface is a sphere. In the same cone equation, you're solving the cone equation, you get phi is pi over 4. That's why phi from 0 to pi over 4. Okay, and what is the theta? Okay, limit for the y, tell you here. Limit y negative third 1 minus x squared until positive third 1 minus x squared. So mean you have the lower semicircle until upper hemicircle, and x from negative 1 to 1 tells you we have the full circle actually. Yeah. Okay, limit for y tell you this is y equal negative third 1 minus x squared. Okay, and the upper curve. In the circle curve, we will cut it by y equals 0. We have two curves, which is y equal to negative third 1 minus x squared until y equal to positive third 1 minus x squared. Okay, limit for x from negative 1 to 1. Okay, the question. Okay, limit for y, x from negative 1 to 1. Hence, it tells you this is a full circle. That's why theta from 0 to 2 pi. Okay, x from negative 1 to 1. So that y from the lower semicircle curve until upper semicircle curve. So from limit of y and x tell you we have a full circle with radius 1 unit. So theta 0 to 2 pi. Okay, solving the cone equation, you get phi is actually 0 to pi over 4. Okay, solving z equal to 1, you get the rho is a 0 to rho equal to secant phi. And then dz dy dx is rho squared sin phi d rho d phi d theta. So integrate rho squared respect to rho cubed over 3. Okay, substitute the rho limit of rho from 0 to secant phi. Okay, so secant power 3 phi. This sin phi d phi. Okay, and then integrate it respect to phi. Okay, again this one you use substitution technique. Secant secant is actually 1 over cos. 1 over cos. So secant power 3 phi is actually your cos. Okay, cos power negative 3 cos power negative 3 phi. So letting the u is cos phi. Okay, u is your cos phi, and then your du is negative sin phi, d phi. Then you get to this answer, where the integral of sin phi secant power 3 phi by using substitution technique. As a previous example, you can get the answer is cos power negative 2 phi over 2. Limit for phi is 0 to pi over 4. And again, cos power negative 2 is 1 over cos squared phi. Then plug in the limit of phi from 0 to pi over 4. Cos k pi over 4 is actually you have sec 2 over 2. Okay. In the okay, cos pi over 4 sec 2 over 2, when you square it, you will have actually 2 over 4. 2 over 4. And then cos 0, you have actually need 1 divide here. Minus cos 0 is 1. Cos 0 is 1. So here, so 1 divided by half will be 2 minus 1. So the 2 minus 1 here. 2 minus 1, we have 1. So you get 1 over 6 integral of the theta. You will get 2 pi. This is the 2 pi here. So 2 pi divided by 6, you get pi over 3. Okay. So we conclude back, okay, for your spherical triple integral in spherical coordinate, where x squared plus y squared plus z squared equal to rho squared, and you use x is actually rho sin phi cos theta, y is rho sin phi sin theta, z is rho cos phi, phi from 0 to pi. If you have a sphere phi from 0 to pi, if you have upper hemisphere phi from 0 to pi over 2. Okay, if you have the cone, okay, cone with the equation z equal to sec x squared plus y squared. Okay, cone z equal to sec x squared plus y squared. By solving the cone equation, you get phi is pi over 4. Okay, to get the theta, actually theta is measured horizontally. Means theta is same with the theta here. Theta measured horizontally. Theta is same with your polar coordinate and spherical coordinate. Okay, with this, thank you for attention and watching this video.